My name is Bjarne Husted. I'm an associate professor at Lund University in Sweden, where I teach at the Fire Protection Engineering program. And today I'm going to talk about fire signatures and their use to detect fires, but I also want to talk about the nuisance sources, which means what other things can cause a fire alarm to go off, even if it's not a real fire. So if you, for example, and it's important to know this in order to avoid false alarm. False alarms are large problems with fire detectors, and many of the, an estimated 2/3 of all fire alarms, they are false alarms. So therefore it's also important to understand how these detectors work. But before I start going into the detectors, I want to talk a bit about flames and the difference between a diffusion flame, also called a non-premix flame, and a premix flame. And to this purpose, I have a small candle. So I'm now going to lighten up this candle, and you see here the candle, you see the flame, and you have the wick, and you see the different colors in the flame. You have it's blue at the bottom, it's blue here at the bottom, and it's yellow. It's more yellow at the top. And what's happened in such a diffusion flame or in a candle is that the heat from the flame heats up the wax. The wax goes up in the wick, and it's evaporate. And so inside the flame you have in fact a high concentration of evaporated wax. Here from the outside we have the surrounding air, and where the two things mix, or just in the thin zone where you have the right properties, the combustion will take place. And this is called a non-premix flame, because the fuel and the oxygen is not mixed beforehand. They are first mixing during the combustion process. And in some way you can say that the air diffuses into the fuel, and that's why it's always sometimes called a diffusion flame. There's a number of distinct features here. Firstly, you see, as I said before, you have the blue zone at the bottom. The blue zone is typically the free radicals burning. That could be O2, O8. Then you have generated a lot of soot, and the soot is unburned carbon particles, and this soot is hot, and it radiates heat, so that is in fact what gives it the yellow color of the flame. So the yellow color of the flame is caused by the soot in the flame. The opposite of a non-premix flame or diffusion flame is a premix flame. I'll just put this out. In a premix flame, which is illustrated behind me, which is picture number 4. It's a fully blue one. You mix the fuel and the oxygen before the combustion. That way you got a much more efficient combustion, and you don't get hardly any soot. So therefore you don't see any. So that means you don't get any soot particles, and you don't get any radiation from these soot particles. So you don't get any yellow colors. The only color you get is the blue color, and the blue color comes from the radiation from the free radicals. And then we have the two pictures in between, 2 and 3, that just shows picture 2 shows a partly premixed flame, and picture 3 shows a nearly fully premixed flame. So we have in these 4 flames, we go from full non-premixed flame in figure 1 to a fully premixed flame in figure 4. A fire gives off different signatures. And I will first start about talking about radiation, because every object which is hot will give out radiation. This is illustrated on these slides. You see the radiation coming from the flame. You get different kind of radiation. And also this radiation travels very fast because it travels with the speed of light. So it means that if you can detect it, you can do a really fast detection. The next slide shows you the different radiation bands. So this is illustrated here. We have for the long wavelength, we have the infrared band. Then we have the visible band, where we can see the light, and then we have the ultraviolet band, which are the short wavelengths. What is radiation from a flame? You have free radicals in the flame, because the free radicals is intermediate products before you get the final products. And typical intermediate product could be carbon, C2. It could be OH, so a combination of oxygen and hydrogen, and CH. So the typical intermediate products before you form the final product. For example, OH could go together with a hydrogen molecule, a hydrogen atom, and then you will form H2O, which is water. So in the fire you get a lot of intermediate products, which then end up in some final products. Further, you have aerosols from the fire, and typically most aerosol from a fire is in the form of soot. This is small, uncomburned carbon, which is in the flame. Lastly, you have some stable chemical compounds, and stable means they will also stay there after a while. The other one is just intermediate. So the stable chemical compound, that is water, which you typically get from combustion. It's CO2, carbon dioxide, and it's CO, carbon monoxide. I want to illustrate the phenomenon of radiation. If you add energy to an atom, you can get an electron to jump from one energy level to the next energy level, as illustrated on the slide. You see the electron jump from the inner and one further into the next energy level. But this is just and these energy levels, they are fixed. So they are fixed energy levels. There is no in between. So these are fixed energy levels. But this is basically an unstable situation. So after a while, just to sum up, the free radicals, they give out energy at fixed energy levels. And as said before, free radicals be C2, CH, and OH. And these radiation is at a fixed wavelength. And these wavelengths are given from 280 to 300 nanometers, 305 to 320 nanometers, 385 to 395, 420 to 440, and 460 to 570. So some of this range is within the ultraviolet range, and some is within the visible light range. So, you also have in the flame, you have aerosols. Aerosols, they typically consist of soot, because as illustrated before, this diffusion flame or fire flames, they are typically not. You don't have a very good combustion, because the air and the fuel has to mix. You don't pre-mix it, so you don't get a very good combustion. So therefore, or good combustion, thereby meaning an efficient combustion. So therefore you get lots of carbon which is not fully burnt. So instead of forming CO2, you maybe just get carbon, C. So the soot consists of carbon, and one feature of this is that the soot is hot, and it will radiates like a black body, and it has. And if you have a high amount of soot, you will get yellow flames. We saw that when I had the light on before, that you have this yellow flame, which is typically the radiation from the soot. And as I said, if you have a premixed flame, you get little soot, you get a blue flame. But if you have a diffusion flame or a non-premixed flame, you get more soot, you get this yellow flame. So, and the stable, but we also have some radiation from the stable chemical compounds, the H2O, the CO and CO2, because temperature is basically just movement of molecules. So a molecule, so temperature is just a movement of a molecule, and a molecule can rotate or vibrate in different ways. They can rotate. They can. Yeah, I shall show it here. This could be a different way that a molecule could rotate, illustrated in this animation. So depending on the mode of rotation or translation, or whatever this molecule does, it will be vibrating in different ways. And this vibration, or this, which is basically heat, or its temperature, will also give radiation in the form of infrared radiation. So when a body which is hot, if you heat something up, it will emit out infrared light. So here we illustrate that this process can emit infrared light. And typically this infrared light that is in the longer wavelength, so we have for these stable chemical compounds, this is the long wavelength. This is light which you're not able to see. So this is more. It's beyond the spectrum of the red light. So this goes from these different levels. But one of the levels which is worth noting at is the level for CO2, because CO2 it has a clear band at 4.3 micrometers, where it will vibrate. So typically carbon dioxide will radiate at 4.3 micrometers. This can be illustrated in this figure. This is for a premixed flame. So here we don't have any soot to disturb the picture. So here you see the relative radiation intensity on the y-axis, and the wavelengths on the x-axis. And you see here at 4.3, you have a clear band showing the radiation from the carbon dioxide, CO2 radiation. So this, in some way, if you have CO2 and if it's hot, you will get a signature in this wavelength. If you then, this was for a premixed flame. If you then take a diffusion flame, you still see some of the same picture, but the view is some way obscured. You see here this is the diffusion flame. You still see a band here about 2.8, but that is in some way overcome by the radiation from the soot. But you still see here at 4.3, we still see a band from the CO. And just to explain a little bit better, if you look at black body radiation, so that means radiations from a perfect black body at 1550 Kelvin, which is typically temperature in the flame, then you will see this pattern. So this is the black this line here, which the black body radiation is the black body radiation. So in some way it sort of dampens it makes it more difficult to see some of the infrared radiation, except if you go to the really longer wavelengths for CO2, which has a clear marker here. Further, another phenomenon of these flames, which you can use to detect fires, is that a typical flame will pulsate. A flame will not be stable, it will pulsate, and will typically pulsate between a frequency of 0.5 hertz up to 15 hertz. So this means that if you can detect, just moving back to the previous slide, if you have a detector which can look at this waveband, and if this waveband at the same time is fluctuating, it's most likely that this will be a signature from CO2 and it will be from a fire. So that is a way of detecting a fire based on, and this was in the infrared, so this was a way of detecting a fire by looking at the infrared bands. So this was just a very short presentation, but I just want to sum up. So fires, they generate different signatures which can be used for detection. It generates smoke particles. We can detect the smoke particles or aerosols. We can detect the heat, which I didn't go too much into, but we can also detect the radiation from the flame. Nuisance sources, they can lead to false alarm. And the nuisance sources can be for the infrared detector. It can be the sunlight, for example, reflecting on water, which is moving, and that can give the impression of it's a flame, but it's basically just the sunlight. And it's important to choose the right detector for the right purpose. And activation of the detector, this can be, I didn't go into this here, but you can see that in the full presentation. Activation time of the detector can be calculated by hand or by computational model. So this is basically my conclusion. I would like to thank you for your attention on fires and fire signatures.